Okay, so here we are. We're asking whether a relationship is linear, and what we've done so far is we've got our null hypothesis that no linear relationship exists, and our alternative hypothesis is that a relationship does exist. Again, very important. The independent variable always goes on the x-axis, and the dependent variable is on the y-axis. Think about this. It is so easy to conflate cause and effect. And it is really on you as the analyst to ask yourself, as a biologist, how do you think this system works? Or what evidence do you have that the system works a particular way? It is very easy to screw this up by putting the dependent variable on the x-axis, or the vice versa, the independent variable on the y-axis. Now let me just also write this out. We can put this, our hypothesis has a linear form. What we're saying is the y variable, the dependent variable, is a function of the independent variable times some linear effect, and then we usually need we add in an intercept, something to kind of modify this relationship a little bit. That's what it looks like in mathematical terms. But you can see that if you mix these two things up, you're going to conflate cause and effect. And that, regrettably, is quite easy to do. It's one of the worst mistakes you can make with this kind of analysis. And it's very easy to do, especially once you start working with the analysis platforms. Okay, so how does this, how do you test this hypothesis? Well, you would go out and you collect a lot of data, and you would think about it, and you would ask yourself, how do I think the world works? How do I think this natural system works? And that's going to help you figure out which one should be the independent variable, which one should be the dependent variable. In truth, as an analyst, it's always good to come back to this, to ask yourself if this is really how the system should work. In some respects, there are some variables that end up being quite safe, like elevation. Basal area of forests do not change elevation. Basal area of forest or density of forest does not change aspect, right? Those landform things you're always going to be safe. You know, elevation is always going to be on the independent, on the x-axis, and then something like, in that case, basal area would be on the y-axis, right? Those things are safe. But something else might be a bit more confusing, such as different levels of canopy strata. One might not be sure which one is cause and effect and which thing is chicken and the egg. So you are warned. Okay, so we want to assess this relationship here. And what we do is, the first thing to do is just simply plot this data. So let's just plot some data. I'm just making up data here, of course. And what we do, a nice thing about, let's just say I went out, I collected a bunch of data, and we can just plot it here in XY space. And what we can also do is there's a relationship that minimizes the distance between each of these observations and the expected relationship given these two variables. And by calculating that, we can get a straight line. So the straight line, the slope here, is the minimization of this distance between the observations and the straight line. In some respects, the straight line, it's not right to call it the mean, but it is our best estimate of the average conditions. So what is the average condition of Y, the most representative condition of Y, given a particular level of X? Well, it's going to fall on this straight line. So we have two things here. We have the amount of information that we've explained by the straight line, And then we have this excess information that we haven't explained, and that's the difference between these two things. This can be summarized with a statistic called the sum of squares. And you can look it up. It's a really fantastic set of Wikipedia articles to read. I know that you're all just hanging on every word in there. I mean, of course, who wouldn't be? Sorry, the lights turned off. 1 second. I'll wave my hands here and try to get the lights back on. That's right. Okay. We're back. So anyway, the reason I mention it is because you can quantify the sum of squares. Make sure I write this in the right place. You can quantify the sum of squares for both the total variance in this data set, and you can also quantify it for the amount of variance that you haven't explained. This is called the sum of squares of residuals. This is called the sum of square total. And if you divide the amount of material, the amount of information that you have not explained by the total information in here, you get this nice ratio, which you can subtract from 1. I'm sorry, it's all crammed together. But what you get here is the statistic R squared. Let's see if that is visible, kind of. Basically what this is saying is if you have very little information here, or residual information that you haven't been able to explain, this value, you say this is 0. 0 divided by some number is 0. So 1 minus 0 is 1. And you may know from your statistics class that an R squared value of 1 or close to 1, like 0.99, is suggests a very strong association between two variables here. What that is saying is that they share lots of variation. The variation in one is quite tightly coupled to the other, suggesting that they're not independent, that one is driving the other, or at least that they're not independent. All right? So, like I said, this doesn't matter that much, but R squared, which is something that most students are familiar with, it has a mathematical derivation, and I feel like I can put it in words pretty easily. There's the total amount of information here, and this is the amount that you haven't described. You take the ratio of that and subtract it from 1, and you get R squared. It's bounded between 0 and 1, and it's the proportion of variance that you've explained with your line. All right, so a couple of things. R versus R squared. R squared is usually the relationship that you learn. You don't necessarily learn it first, but it might be the one that you use the most. R squared and R, which is R is this correlation coefficient, they end up having a relationship that kind of looks like this, like that. What would seem like a fairly high correlation value, R value, may not actually be a very high R value, and that's because you're squaring these together. When you square a small number, you get an even. When you square a number that's less than 1, you get an even smaller number. And if you square 1, you get, this is 1, right? That is equal to 1. So what this is saying is R squared is, it's really nice because it doesn't have this problem that R has. And that's that above some level of R, depends on your data set, but some level, sometimes, like 0.3 or, should we just down here, 0.3 or 0.4. Basically, you're just kind of, the correlation is just kind of giving you random noise. If you have a lot of data, like hundreds of observations, you might find that correlation as low as an R squared as low as 0.2
might be telling you something, might be telling you that there is some association here. But like I say, you need a lot of data in order for a weak relationship like that to be clear from your analysis. One of the hard parts about this kind of linear analysis is, and this is true not just for you trying to do this assignment, but for anybody doing linear analysis, it's easy to tell a really strong effect from nothing, but it's hard to tell a weak effect from nothing. And that's just like a general problem within statistics. Okay, so we still haven't gotten to this ultimate thing here, which we're trying to understand whether a linear relationship is real, whether there is a linear relationship between two variables here and or not. I haven't answered that question. And what we can do through the use of two techniques that are related but different, one is correlation, the other is regression, we can actually get to this and then ask a formal hypothesis here, or do a formal hypothesis test. Do we have a linear relationship here or not? So as I said, we've got our data set. We can draw our line here in it. I've drawn a data set here that has a pretty strong, looks like it has a strong association. We can derive an R squared out of this, and then we can do a formal hypothesis test, which in this case is our model again. What we're asking here, make sure I get this, fit this in here. Essentially what we're doing in the null hypothesis is we are asking, the expectation here is that beta 1, the slope is no different, is not equal, or is equal to 0, or cannot be distinguished from 0. That's what we're saying. Whether the alternative hypothesis, and we're not saying whether the slope is positive or negative, whether the relationship is positive or negative. We are saying that this is something other than 0. It's not equal to 0. And the way that we determine that is by how much information is in this and the strength of the association. So the R squared value cannot answer this for you alone. It gives you insight, but it cannot answer this alone. You need some sort of decision rule about that allows you to say there is enough evidence here that I can reject the null hypothesis, or I cannot reject the whole null hypothesis. One of the common mistakes that students have about null hypotheses is they'll say, well, we have to accept the null hypothesis. You never accept the null. The null is never true. You simply do not have enough evidence to reject it. One of the frustrating things, super confusing things about this kind of statistics is that in a lot of respects, it's asking you to prove a negative, or it's kind of confusing. It seems like it's trying to prove a negative. It's not really doing that. It's just simply asking, at its core, how confident you can be that you would have this, you would conclude that there is a positive or there is a significant relationship between your two variables when in fact there is not. Did that sound confusing? That's because it is. It's, ultimately what happens here is that we come up with a level of confidence about how likely it is we got this strength of association, or we concluded that there was a relationship here when in fact there was not. That's the p-value. – That's a mouthful. That is a huge mouthful. Like, I don't even have marbles in my mouth, right? There are no marbles in my mouth. And it feels like I'm talking with marbles in my mouth because that's just so kind of convoluted. Now you have heard about p-values, and if you already get this, great. In general, what we do here is we, through doing this analysis and extracting the sum of squares and doing some other stuff here, we can come up with a probability that we would conclude, that we would find this level of the strength of association based on a random draw of our data. So this is saying, based on a random, you went out, you collect this data, you estimated this relationship, and if you were to then sample it at random, randomly sample from a bag of data that is drawn from the same distribution as the data set that you collected, yes, that is a mouthful, that you would get this level of association. So how likely is it that at random you would find this level of relationship when in fact it didn't exist? That's what the p-value is telling you. So this, of course, I've drawn a strong relationship here. And let's say that the R squared is strong. Let's say that it's 0.75, probably is. We would have a very small p-value in this data set. 0.0, let's say it's 0.01. What this is saying is that in 1,000 draws at random, we would find this level of association, based on a random draw. We would find this level of association when in fact the relationship between the dependent and the independent variables did not exist. Very unlikely. Very unlikely. There is sufficient evidence here to reject the null hypothesis. We would say there's actually a relationship here. This is a strong linear association. This data seems to be, these two factors seem to be linearly related in our data set. Now where things get kind of murkier is when the p-value, say for some other relationship that's not as strong, you have a p-value of 0.1, or you have a p-value of 0.005, or let's say you have a p-value of 0.2. So those of you who have taken statistics, and I think it's all of you, when do you think you would have sufficient evidence to reject the null hypothesis? When do you have sufficient evidence to reject the null hypothesis?
When the p-value is greater than 0.05?
Greater than 0.05?
Less than 0.05.
Less than 0.05. Okay. So 0.05, p-value of 0.05 means that 5% of the time you would get this level of strength of association based on a random draw of your data. So 1 in 20 times. It's not especially common. Why do you use 0.05?
I think it's just a standard that like they taught us in stats. I mean that like for the medical field, I think they use 0.01 or 0.001 because they want to be absolutely certain that like the drug or whatever is working. But I think 0.05 is just a good standard for everything else.
I mean, it's, 5% of the time is not very common to get it wrong based on a random draw. So yeah, there's that. But it is a standard, but where did it come from? Anyone other than Morgan have an opinion about 0.05? Your opinion?
It's just the 95% confidence interval.
Well, it's not because of that, but I kind of think that the 95% confidence interval ends up being because, we use 0.05 as a significant level. So 95% confidence intervals are something different. They're related, but they're something different. So yeah, I wouldn't be surprised if that's why we have 95% confidence interval. But still, where did 0.05 come from? They didn't tell you this story in statistics? Who'd you take statistics from? Oh, you are so impoverished. Oh, you poor guys. Oh, it's just a really inspiring story. A story of like heroics and, sacrifice and the goodwill of humanity. No, it's none of that. It's just a bunch of crap. It's arbitrary. It is absolutely arbitrary number. There was a copyright dispute, and two values could be adopted or could be used without infringing on copyrights, and the two that were chosen were 0.05 and 0.01 because they're fairly small. Yeah, it's pretty weird. You learn 0.05, of course you do. I did too. We all do. And it works because it's not very common. It's 1 in 20 is not very frequent, but it's arbitrary. And in fact, particularly over I've noticed this over the last 10 years, although it's a trend that's been going on for the last 30 years or so, this whole framework is changing. What we're doing here is we're trying to disprove this null hypothesis that no relationship exists. More modern statistical analysis is asking what is the strength of evidence that we have for a specific relationship? It's a lot easier to say, and I think that as the technology improves, it'll probably be a better framework for understanding the world. For now, we learned this kind of frequentist statistics. That's what it's called, traditional hypothesis testing, because it will help you learn other statistics. It will help you learn other kinds of data analysis. It does work in that way. It's just like, oh, geez, man, it is a mouthful to actually say in words what this stuff is doing.